Thanks a lot for having me. Really happy to be here after Spock movie. So I'm going to talk about some few recent papers of mine, which are all the same general theme, which is deriving dualities in lower dimensions by compactifying dualities in higher dimensions. And so obviously there's many dualities that have been found in the last couple of decades in various dimensions, with various amounts of supersymmetry. And there are lots of known relations between them. For example, by compactifying the 6D theory, we know that lots of the lower dimensional dualities can be derived. But these relations, there's also relations involving dualities which are so-called IR dualities, where you have some UV descriptions which are not equivalent, but they flow to equivalent fixed points. And here the relations between dualities in different dimensions are a little bit more subtle. So let me just give an example to illustrate this. So in 4 dimensions, we have a version of cyber duality involving SP gauge groups. So this theory still works for this one. And also with some mesons and a superpotential. Okay. There's a 3D duality that's very similar between n equals 2 theories. So the first theory is just the 3D version of this theory, of the first theory here. And the duality here is a little bit different. Now there's, in addition to the mesons, there's an extra singlet chiral Y and a superpotential, which involves a coupling to a certain monocle operator. And note also that the shift of the dual rank of the gauge group is also different. And finally, there's another, so this is due to Aharoni, this is due to Intriligator and Kudil. And then there's a duality in 2D to Corey, which is again very similar, but also slightly different. And here the duality is with a still further difference in the shift of the rank. And here I demand that 2NF be odd, so that this makes sense. So there's clearly some relation between these dualities. They all look very similar. It's hard to imagine they're not related. But it's also clear that they're not related by just dimensional reduction. How do we explain these shifts of the rank and this funny superpotential? So the problem is again, that these are IR dualities. So if we try to just naively dimensionally reduce both sides, these theories are not equivalent in the UV, so when we reduce the UV description, there's no reason to expect them to be equivalent. So we have to be a little bit more careful. So let me make a little diagram. So in general, we start with some UV description here in V dimensions, and we flow to an IR fixed point. If we have a IR duality, we have 2 theories that flow to the same fixed point, and if we were to then dimensionally reduce this and get some d-1 dimensional theory, these would be equivalent. Whereas if we first dimensionally reduce and then flow, we get something different. This diagram doesn't meet. So what we would really like to be able to do, and my goal in this talk is going to be to construct some purely d-1 dimensional UV description, which I'll call T hat, which flows to the same fixed point as we get by reducing the IR fixed point in d dimensions. If we're able to do this, then this means that given an IR duality in d dimensions, we get for free an IR duality of these theories in d-1 dimensions. So the goal in this talk is going to be to construct these t-hat theories and then apply this to dualities.
So the construction of t-hat is gotten from TUV. And for each description of the UV d-dimensional, you'll get some t-hat.
Yeah, so the hope is that there's some sort of map from d-dimensional descriptions to d-1 descriptions.
And the dimensional reduction is just plain old dimensional reduction where you erase a dimension, or do you, I mean, you could do compactifications and you could worry about, or?
Well, yeah, so I claim that if I have an IR theory, then those would be roughly the same. The naive reduction, because the size of the circle shouldn't matter in a formal theory.
There are other things that can be done, twists around boundaries.
Yeah, so, well, in the first two cases, I'm just reducing on a circle and there's nothing special. In this case, which I probably actually won't have time to say much about, there is some extra twist that I do on the sphere. So, and then they say a few words about that at the end.
But somehow you already know that the infrared of those theories are related by dimensional reduction or not. You say both flow to the same infrared, and if you dimensionally reduce, you get the other one, or they are both related?
You're saying between these two realities? So these are not related by. So these are not going to be the t-hat theory. So I'm going to. I'll say a little bit more about this.
No, I'm saying the above and 40 you have an infrared theory of those two that describes the infrared of those.
Right.
In the 3D you have an infrared of those. So you already know that the infrareds are related, as you said there, or?
In this particular example,
No.
the 3D infrareds are not the dimensional reduction
No.
of the 4D.
No, they're not. Yeah, I'll explain that in a little while. Okay, so the plan of the talk, the rest of the talk, I'm going to review the story from 4D n equals 1 theories to 3D n equals 2. I'm going to say a little bit about, well, I'm going to talk about 3D n equals 2 going to 2D n equals 2 Tomlinson theories. And then I'm going to say some words about supersymmetric partition functions and how we can use those to also study this problem. Okay. So before getting into this, I just want to review a little bit of background on these theories, the 4 supercharges in various dimensions. So I'm sure this is familiar to everyone, just to get on the same page.
There are also sliding blackboards behind if you want to use them.
Okay. So, the cases are going to be interested in 4D n equals 1, 3D n equals 2, and 2D n equals 2 comma 2. So these are all have 4 supercharges. They're all related by just dimensional reduction, going that way. And so let me say a little bit about some details that I'll need. So first of all, the fields are chiral multiplets. So some complex scalar and fermion, and these exist the same in all dimensions. Then there's the vector multiplets. So, in 4 dimensions, we have the gauge field and gaugino into the scalar. In 3 dimensions, the 4th component of this gauge field is going to become just a real scalar. And in 2 dimensions, you get a further scalar, which usually combine into a complex scalar, sigma tilde. These scalars are going to play an important role. The actions I'm going to use are the usual actions, Yang-Mills action, so some superspace, usual Yang-Mills action and kinetic terms of the scalar and the superpotential. And this is basically the whole story in 4 dimensions, and there's similar actions in 3 and 2. But in 3 and 2, you have some additional features, which let me write them here so it's not too low. So in 3 dimensions, you have Chern-Simons terms. So these look like just the usual Chern-Simons terms plus some extra fields involving the extra terms involving the other fields. And in 2 dimensions, you have another additional feature. So in addition to chiral fields, I should say, you also have twisted chirals. Which have the same field content, but they're just acted on slightly differently by the supersymmetry algebra. And in addition to the superpotential, you have a twisted superpotential, W tilde, which involves the twisted chiral fields. Okay, and then the last thing I'll need is real masses and twisted masses. So these don't exist in 4 dimensions, but again in 3 and 2 dimensions, you can turn on, I'll just say it in words. For each flavor symmetry, you can couple a background vector multiplet. You can weakly gauge this flavor symmetry. And you can turn on a constant value for this sigma in 3 dimensions or the sigma tilde in 2 dimensions. And this acts as a mass. It gives a mass to all the fields which are charged under this symmetry. So this is another way you can, another tool you have when running actions is to turn on these background gauge fields in these constant configurations. So let's now go to the first example, which is going from 4D to 3D. So let's take a 4D n equals 1 gauge theory. And let's assume that it's, say, asymptotically free, and it flows to some nice supernormal fixed point. So a good example to have in mind is SUN UCD with NF flavors, NF fundamental chirals and fundamental chirals. Okay, now we place this theory on a circle, R3 times a circle of radius R. And then at low energies, at energies far below the kk scale, 1 over R, this is has an effective description as a 3D n equals 2 theory. And what we want to do is we want to engineer a purely 3D description that flows to the same effective description. So let's try to understand this effective description. So, first of all, if we take R to be very large, or sorry, very small, so the kk scale to be very large, and very large means, say, compared to the lambda QCD. And this means that at the scale where we compactify the theory is still very weakly coupled. Right? It's asymptotically free, so it's nearly a free theory. And so to a very good approximation, we're just doing the naive dimensional reduction with no subtlety. Interactions between the kk modes or anything. So we have an approximate description as just the naive dimensional reduction. I'll call that NDI. So just the 3D n equals 2 gauge theory with the same gauge group, the same matter content. But this is only approximately true. There are corrections to this. So the first correction is that, remember this real scalar sigma in 3D comes from the 4th component of the gauge field, or in this case, the component along the circle. But now, because this circle still has a finite radius, sigma is identified with sigma plus 2 pi over r. So it's no longer a real variable; it's periodic. So that's the first difference from the naive reduction. And as r goes to 0, taking it to be real is a better and better approximation. And this implies another important difference, which is a certain non-perturbative effect. And to understand this, it's useful to let me just briefly review some facts about purely three-dimensional gauge theories. So in 3 dimensions, you have a Coulomb branch. So now I'm temporarily in an ordinary 3D n equals 2. Then you have the Coulomb branch, which is parametrized by the eigenvalues of sigma. But it's also on the Coulomb branch, the gauge group is broken to the maximal torus, and so you have an abelian 3D gauge theory, which can be dualized into a periodic scalar. So these are the dual photons. So the Coulomb branch is rank G complex dimensional, parametrized by these guys, and in fact it's natural to define a certain combination which semi-classically far out on the Coulomb branch has this form. Where alpha is some root of the gauge group, and we've exponentiated these guys, and this is the semi-classical expression for this operator, which is a chiral operator. So these chiral operators, which have a more complicated expression as you get closer to the strongly coupled region of the Coulomb branch, but they remain chiral operators, and they parameterize the Coulomb branch of the theory. So in say pure SU2 with no matter, then it was shown by Affleck, Harvey, and Witten that there's a superpotential which is generated by instanton effects into monopole configurations, which is the form 1 over y, where y is the operator parameterizing the SU2 Coulomb branch. And so this theory has no stable vacuum. In 3 dimensions, superpotential run away. And in the general gauge theory, the semi-classical Coulomb branch, most of it is lifted by very similar effects, so it's a similar superpotential. So there's some, I won't write it in detail, but there's some sum over some of these roots alpha of 1 over y, alpha, which lifts most of the Coulomb branch. And you can think of these as arising as when I go to a place in the Coulomb branch where 2 of the eigenvalues are coming close together, I'm getting an enhanced SU2 there. And so I'm locally in this situation, and so I expect to be driven away from that point. So now we can go back to the theory on a circle. And this, the periodicity of sigma implies a relation that, well, it implies that, as I was saying, these terms are generated when 2 eigenvalues are coming close together. But now I can have an eigenvalue which goes around the circle and meets another eigenvalue because of this periodicity. And if you work out what this means, there's an extra term in addition to these terms, which is the form eta y, where this is a certain, this is the maximal root in the gauge group, and eta is related to the radius as follows. So again, you can see that as the radius is going to 0, this effect is going away, and we're approaching the naive dimensional reduction. So this is the effective description of the theory at low energies, of the 4D theory on a circle at low energies, and this extra superpotential term is driving us to a different fixed point than the naive reduction takes us to. So now we can guess, or we can more or less, we have a good guess for the T-hat theory. It's equal to the naive dimensional reduction plus the certain superpotential, which is going to reproduce this superpotential at low energies. And the answer is that you should take this this operator is this is an operator which creates a monopole, so it's a defect operator. It says that at a certain point in space, you impose a gauge field has a monopole singularity. And it turns out that this flows exactly to this chiral operator, parameterizing the Coulomb branch at low energies. So the claim is that this theory modified by this superpotential. So this is now a 3D UV description, flows to the same effective theory as the 4D theory on the circle.
So that non-contributive clean, can that be generated by monopoles?
No, this we're putting in by hand, right? We're
No,
just
but I
saying.
just wondered the NY there, what generates that? Is it associated with topological?
Yeah.
Okay.
By monopole configurations
Okay.
that you sum over in the path.
Oh, I see.
Smooth monopoles. So that here we're inserting a singular monopole configuration. Okay. So this is the prescription, and so now we can use it to try to derive new duality. So if we go back to the
So, is this a kind of a UV complete description, or is I'm supposed to think of this as a microscopic but still effective description? I need some sort of cutoff to tell you, some categorization to tell you what this monopole is.
Yeah, it's a little tricky too. I mean, you could ask this question. There's lots of examples of 3D theories with monopole superpotentials that people study. You could always ask this question, and yeah, it's a little tricky. Probably you need to define it with some kind of cutoff. Yeah. But
Does the naive dimensional reduction flow to a CFT?
yeah.
So if you take that CFT, then the extra thing, the monopole operator, is just some ordinary chiral operator in that CFT.
Right.
And if you perturb that thing by that superpotential, then it will flow to this same infrared as we see that theory.
Yeah, I think that we should.
So that would be what we're defining as the
Right. But then you're using the strongly coupled IR fixed point then. So yeah, no, this is already.
So, but I'm a little confused by that. I thought the naive dimensional reduction didn't have a stable factor.
Sorry, that was the pure SU2 theory with no matter. Once you have matter.
Oh, once you have matter.
Okay. So now if we take Seiberg duality and we apply this prescription to it, by this general logic over here, we should get a 3D duality. So that duality is SU and C and layers, and a superpotential is dual to SU and F minus NC. The corresponding potential, and also the mesons. And this duality actually does work. In a little more detail, what failed with the duality without the superpotential was that the Higgs branches match because they're basically the same as the four-dimensional Higgs branches, but the Coulomb branches don't match up. But these superpotentials, they basically do freeze with the Coulomb branches, so they throw away the bad part, and then you're left with just the Higgs branches, and those match, and you can check everything matches. So this is a new duality, but maybe it's not that interesting. I mean, you'd be more interested in the duality for SUN DCD without this superpotential. And it turns out once you have this 3D duality, you can play purely three-dimensional games, such as adding real mass deformations and flowing and seeing where you flow. And I won't go through all the details of it, but by doing that, it turns out you can get rid of the superpotential and find a dual of SUN, of the naive dimensional reduction. The dual's description is a little bit messy. So the claim is that SUNC with NF flavors and no superpotential is dual to the following theory: UNF minus NC with NF flavors. And as usual, the mesons, but also some fields B, C tilde, and Y, which are in the determining bar, and this is a singlet. And the superpotential two monopole operators that parameterize the UN Coulomb branch. So, okay, it's not the nicest dual description, but you can check that these two theories are dual.
So this gives a dual of SUN, UCD, and three dimensions.
And you can run the same machine on your favorite 4D duality, and you can deal with different gauge groups and different matter content. And for example, you can derive the 3D SP duality that I mentioned. Okay, so that's all I wanted to say about 4 to 3. And then now move on to 3 to 2.
Is there some master set of dualities in 4 dimensions that you could assume you get all known IR dualities in 3D?
I think it's hard to get 3D mirror symmetry from 4D. I don't know how to do that. You could probably get
N equals 4?
either one, yeah. N equals 4, yeah, the N equals 4 set.
Sometimes people call these N equals 2 IR dualities also.
Which one?
Sometimes people call all of this 3D N equals 2 things also mirror.
Okay.
Which
So,
do you mean?
well, there's N equals 4 mirror symmetry,
Yeah.
and then there's N equals 2 deformations of it. So by mirror, I'll talk about mirror symmetry in a little while, but by mirror symmetry I usually mean something which exchanges particles with vortices.
Okay.
So that doesn't happen here. But yeah, so those kinds of dualities, I don't know you can get them in 4D by studying boundary conditions, of like N equals 4. But I don't know how to get them by dimensional reduction. Okay, so next I want to talk about 3D N equals 2 going to 2D N equals 2. So before going into this, I'm going to need to review some facts about 2D N equals 2, theories. So remember I mentioned that you have twisted chirals in 2, and an important example is the field strength twisted chiral, which the bottom component is the complex scalar, and it also contains the field strength. So it turns out this is a twisted chiral multiplet, and so it can appear in the twisted superpotential. And a common way that it does is as a linear term, where if I write this in T is some complex parameter, and if I write this in components, it gives me the Fi term and the theta angle. So these get combined with a single complex parameter in 2D. And in addition to this superpotential, you can study, a very useful object to study is the effective twisted superpotential, which you get by integrating out all the charged chirals coupled to the gauge field. So you pick some background value of sigma and you integrate out all the charged chiral multiplets, and you can compute the effective twisted superpotential which is generated for sigma. And for a single charged chiral, this has the following form. And this is exact. And so let's take an example. So if I have, say, some U1 theory with chirals of charge QA and maybe mass MA, so twisted mass MA, then I get some twisted superpotential. Let me write its derivative. So the usefulness of this thing will be that you can find the vacuum of the theory by finding the zeros of its derivative. So the derivative of this thing is this, and then we also have the Fi term. Now there's a slight, so to find a vacuum, you would normally look for the zeros of this. But there's a slight subtlety because this twisted chiral is not completely unconstrained. The field strength has its flux is quantized. So we have to impose that with the Lagrange multiplier, and after working out what this means, you find that you only need to solve this equation, mod 2 pi I t. And so it's equivalent to just solve this equation. But then this gives a very simple polynomial equation. So you can immediately count the vacua in this theory by just computing the degree of this polynomial. So if some of the QA's are negative, just move it to the other side, and you have a nice polynomial equation. You can also do this for non-abelian theories. So another example is a UNC with NF limited. So here, you can take sigma to be in the Cartan, so you have some eigenvalue sigma I, and you can compute this for each eigenvalue, and you find a polynomial equation for each I. Now, because this is a non-abelian gauge group, we should only count solutions mod Weil symmetry, and you should also not count solutions where you have two eigenvalues sitting on top of each other, because then you have some enhanced non-abelian symmetry, and it turns out that these theories break supersymmetry, so these vacua are not really there. So you should only count the distinct solutions mod Weil symmetry. So basically, just pick NC distinct roots of this polynomial, which has degree NF. So you can see that the number of vacua in this theory is just NF, choose NC. Now this theory has a dual description due to Domini et al., where it's a Seiberg-like duality to UNF minus NC with NF flavors and mesons, and so this is a very simple check of that duality. Okay, so getting back to the reduction, so why is this effective twisted superpotential useful? So much as we did in 4 dimensions, we found we looked at an effective superpotential on the Coulomb branch and used this to construct some UV description by finding a purely 3-dimensional description which had the same effective superpotential. So here we're going to do the same thing. We're going to look at the effective twisted superpotential of a 3D theory on a circle and try to find a 2D theory which reproduces this. So let me tell you about the effective twisted superpotential of a 3D theory on a circle. So we take 3D n equals 2 on R2 and the circle of radius R. And let's start with just a chiral bit, which is, and let's couple it to some background sigma, which is just another way of saying turning on a real mass for this chiral. And also we can turn on a constant value for A3, so some polynomial along the circle without breaking any of the supersymmetry. So let's do that. Then the claim is that this, if we think of this 3D theory in a circle as a 2D theory with infinitely many KK modes, we find that this has 2D chirals, which with twisted masses so that the KK modes have masses which scale as 1 over R, and these combine with the bare masses that we turned on in this way. Now we can just use this formula that I wrote to compute this effective twisted superpotential by just summing over all these modes. So let me call this sigma tilde, which sits in some twisted chiral sigma. And we want to compute, and I'll just compute the derivative. We sum this over all the KK modes, and you find that it's a simple form. And here I should mention that, as we saw in 4D, this sigma, this A3 is periodic on a finite circle. So this amounts to a periodicity. Sigma goes to sigma plus I over R. What you can see is, well, it's almost consistent with this. It's actually changed by a sign, but that's because the pure free chiral actually has a parity anomaly, which is responsible for this sign. But in the theory, without a parity anomaly, the superpotential would be invariant under this. Okay, so let's get to an example. Oh, and one more ingredient I need is the contribution of a Chern-Simons term to this superpotential. So let me denote it with this superscript R to denote that on a finite circle. So for a Chern-Simons term, I have a contribution like this for a level K Chern-Simons term. And for an Fi term, I have a contribution like this. This is the Chern-Simons level. This is the Fi level.
So, is there the effective superpotential generated on the circle? Is it also, does it have an interpretation like generated by some topological configuration, or no, like monopole special like it does in going from 4 to 3?
Well, I just...
Either what superpotential as interpretation.
Right.
Generated by the KK.
Yeah, no, it's not a non-perturbative. Right? It's the 2D superpotential. Well, it comes from just summing the 2D effective twisted superpotential, which is a one-loop computation. And so this is just summing that for all the KK modes. Okay, so let's do an example. First example, we'll take the U1 theory, with K equals 1, and charge plus or minus 1. And we have with a common mass M and an Fi parameter. Zeta. So the effective potential. Write it out. Okay. Now, what we want to do is study this theory at energies far below 1 over r and see the effective description. So equivalently, we can fix the 2D scale and take the 1 over r goes to 0. So we want to study the r goes to 0 limit of this superpotential. And let me guess the answer, first of all, or guess a plausible answer, which is that we just get the 2D version of this theory. So U1 with charge plus or minus 1 chirals, the effective twisted superpotential there is just this. And if you stare at this, you can see that as I take r to 0, I get this. So I can approximate as just the argument, take a linear approximation, and then the log r's cancel. This term is going away, so the Chern-Simons term is just getting completely washed away. And this term, we'd like to go over to this term, but in order to do that, we need to take 2 pi r zeta equals t, So we need to scale zeta as 1 over r, the fi term. But if we do that, then as r goes to 0, this is the effective persistent potential here is going over to the 1 for this, what they call it the naive dimensional reduction, where we're just throwing out the Transillian term. And so I claim that if you take this limit, so m finite and zeta as scaling as 1 over r, then we get the t hat. In this case, is just this u1 u2. Okay, but this is a little bit strange. So and this argument that I'm about to say was originally made by Agonadich et al. In a paper from a few years ago. So I'm just going to review that. It's a little bit strange because of mirror symmetry. So this theory has a mirror dual. So 3D mirror symmetry. So this has a dual description as a U1 theory with k equals -1, 2 charge 1 chirals with masses plus or minus zeta, and fi term m. So the characteristic feature of mirror symmetry is that masses and fi parameters are exchanged. In 3D theories, they really should be thought of as on the same footing, and they're exchanged by mirror symmetry. And but now, because we treated them very asymmetrically, in order to get a nice gauge theory on this side, we're going to get something much stranger.
So just remind us, for in 3D n equals 2, the mirror symmetry is like when you say a dual, that's like a cyber dual in the sense that they share an infrared fixed point, but they're not equivalent.
Yeah. So I should say 3D gauge theories are with the Engels term are not conformal. They're never conformal. The Engels term is relevant. The gauge coupling is relevant, and so they typically flow to some stronger couple field theory and infrared. And so the duality is between those stronger couple theories. Okay, so what happens if we take the r goes to 0, so we can compute the effective crystal superpotential of this theory, and I will write it down. It looks a lot like this, except now zeta is appearing here and m is appearing here. And what you can find is the solution, so we call it sigma star, the vacuum solution, so solution to e to the w prime is 1. Is behaving, so you can think of this as the bev of sigma in the vacuum, is behaving as log Rm over 2 pi r as r goes to 0. So it's diverging. And so what this is telling you is that sigma is not a good variable to describe this theory. What we need to do is rescale it somehow so that we have a regular description of the theory. We need to define a new variable. And the natural choice, well, a choice that makes the bev finite is following. For him, here mu is some arbitrary 2D scale, which we need to introduce because this y turns out to get some logarithmic normalization. And then you can compute that y has a finite bev as r goes to 0. So y is a better variable to describe the theory.
Right. So sigma stars is the vacuum that you find of the mirror dual here.
Yeah.
So don't you, maybe I'm off, but because in the previous case the limit that you've taken was r rho constant, right?
Yeah.
The zeta, yeah, sorry. And don't you expect the right limit to take in the mirror dual too?
Well, I don't have a choice. I want to, whatever I do on this side, I should do the corresponding.
The m on this side is the
yeah.
It's the fi term.
Right. Yeah. So that's why So here I've mapped
Oh,
the
sorry, I
mass
didn't know that.
parameters
Oh,
by the
it's-
duality.
So M is actually the FI term on the.
Yeah, I read it. It's a little confusing. I write it as M because
Okay.
I already defined that.
No, yeah, that's good. Nice.
Okay, so now we can, in terms of Y, we expect that the twisted superpotential should have some regular limit because its solution is staying at a finite value. And you can compute that as R goes to 0, you get the following thing. In reading order, you get this funny looking twisted superpotential. So now our guess at the T-hat theory is to just take a Landau-Ginzburg model with the basic field, which we'll call Y. And I should have said that Y, because sigma was periodic, sigma goes as sigma plus I over R. Y has a period which stays finite as R goes to 0. So Y has a periodic imaginary part. So when we take as our UV description a Landau-Ginzburg model with a twisted chiral with periodic imaginary part and with superpotential, which we're now taking as our UV twisted superpotential, which is exactly this. I won't write it. Getting my decision correct. And then again, we expect that this has, well, trivially the same low energy description as this theory on a circle. And so the claim is that this is the correct T-hat theory here. But now, and again, this is already pointed out by Agnev-Shell, what we've shown is that 3D mirror symmetry goes over to this duality, which is just 2D mirror symmetry. This is Horry-Vafa duality. It relates abelian gauge theories to Landau-Ginzburg models involving twisted chirals, which have these kind of exponential superpotentials. So this is a special case, but for every 3D n equals 2 mirror symmetry, you can apply the same argument and you get all of the Horry-Vafa dualities. So Horry-Vafa duality is implied by 3D mirror symmetry. Okay. So now I want to do another example.
Well, you said that you don't expect the 3D mirror symmetry is implied by any pudding.
Right. That's what Okay, so now let's do a Seiberg duality. So let's start with the following theory. UNC with the Chern-Simons level K and NF layers. So let's start by writing the twisted superpotential. So as we did in 2D, we diagonalize sigma, and for each eigenvalue I, we find the following thing. Okay. So let's start by finding the vacuum of this theory. So we need to solve this equation. And it's useful to define some new variables, so let's define xi is e to the 2 pi r sigma I. And this is really the appropriate variable to use because the imaginary part of sigma is periodic. So this xi is the single value for everything. And also for the background fields, we have, say, UA And then you can massage this after exponentiating, you get, again, a polynomial equation. And now in terms of these exponential variables, yes. So this is a polynomial equation, and as before, we just need to take the NC eigenvalues to lie among the roots, and we can see that because of the Chern-Simons level, let's take k to be positive. So this has degree k plus nf, so the number of vacua in this theory is k plus nf times nc. I should just say that this twisted superpotential written in this polynomial form is a really useful object. You can count these vacua very easily in 3D. And it's also related to the chiral ring generated by these relations gives the algebra Wilson loops in 3D. So it's a useful object. Okay, so, and also this, I should mention that this theory has a dual description to the incapacitative duality, where it's dual to u k plus nf minus nc level minus k with nf flavors and mesons. And again, this is a very simple check of that duality. And you can see that the Chern-Simons term plays a very important role here in the dual rank. And it was necessary because the counting of the vacua is kind of on the check side. So now we want to take this down to 2D. So again, I'm going to write a guess, and we'll see if it's right. So the guess is that we just are going to end up with the UN theory, 2D UN theory with NF flavors. And by exactly the same argument as I said before, that these are going to go over to just logs as r goes to 0. And if we, as long as we scale so that 2 pi r zeta is t, the Chern-Simons term is going to again get completely washed away, and you're going to get this effective twisted superpotential of this theory. But given what I just said about giving catastrophic duality, this is very strange. Because if I do this on this side, I get this U minus C theory. And on this side, I would get UK plus NF minus NC. But now K is just a free parameter, right? So this is telling you that basically every 2D theory with the same number of flavors is dual, which is clearly not true. Well, it's not true. It's not clear. Well, there's another problem. So remember that I told you this theory has NF choose NC vacua. And so this theory has a lot more vacua. And where did the extra vacua go? So these two questions are related. So it turns out if you study this, well, I just erased the polynomial, but if you study where the zeros of this polynomial are, you find that the solutions, there are NF solutions at finite sigma, which are just the, sorry, as r goes to 0. There are NF solutions at finite sigma, which are just the zeros of the twisted superpotential of this 2D theory. But then there's a further k solutions, which are staying at sigma of order 1 over r. why I can show this really briefly. So remember the polynomial we found had the schematic form. If I take x to be, if I take the masses towards 1, I get something like x minus 1 to the nf. Sorry, I'm taking the masses to be finite, so mu a's, which were e to the 2 pi r, times the masses are all going to 1. So the polynomial is looking something like this. So I have nf solutions which are also going towards 1, so sigma is staying finite. But then I also have, when I get rid of those, I have k solutions which are distributed around the unit circle. So sigma is staying of order 1 over r. So I have these k solutions that I should also keep track of. And so what I can do is, for each L from, say, 0 to nc, I can pick L of the eigenvalues sigma I to sit among these large solutions. And then the remaining n minus L, nc minus L, are staying small, and they're going to be governed by this superpotential of the 2D theory, which is the superpotential when I have nc minus L eigenvalues is the same crystal superpotential as a unc minus L theory with nf layers. But here, again, I can let L vary, and so the claim is that the correct t-hat theory is given by a direct sum of theories. So there are many examples in 2D of UV descriptions which flow to direct sums of CFTs. So for example, if you take an n equals 4, 4 gauge theory, the Coulomb and Higgs branch completely decouple, and you get a direct sum of the CFT on each one. And what I want to claim here is that this time our UV description is a 3D theory on a circle, but again we get this behavior where at low energies it's decoupling into a direct sum of theories. And first of all, this corrects the vacuum counting, because I just add up the vacuum for all these theories, and you can check that it gives all k plus nf presents. Sorry, this should go up to k, so there's only k eigenvalues. And if this ever gets negative, then you run out of I just won't like this. So it gives the right counting of vacuum, but it also is nicely consistent with the incapacitive duality. So if I start from one side, I get UNC and the dual side, I get a similar thing. And you can see that these are related term-wise by this duality of Benini et al. That I mentioned earlier, where NC goes to NF minus NC. So this is the resolution of this contradiction that we found. Okay, so these are a couple simple examples of what you can do by studying the twisted superpotential. Let me just mention a few other results you can find. So you can try this for n equals 4 abelian mirror symmetry. So n equals 4 abelian mirror symmetry does not follow from the n equals 2 duality that I mentioned earlier, where I got the word Laffa. So this is an independent duality in 3D, but sadly, this just gives, again, Hori-Laffa duality. It doesn't give anything here. Another example is you can start from the following 3D duality. SUNC with K equals NF minus NA over 2, and NF fundamentals of NA anti-fundamentals. Let's say NF bigger than NA. This is the chiral theory in 3D, and this can be derived by flowing from the duality I mentioned earlier, the SUN duality. Sorry, this is dual to SUNF minus NC minus K NF NA and NF times NA mesons. And this implies the 2D duality, which is just more or less the naive reduction more or less works in this case, although you have to do some analysis to affect that. But it's SUNC NF NA goes to SU NF minus NC. So this is a new 2D duality. It was a 3D signal. And you can do lots of checks in 2D. You can check that the elliptic genus matches, and so this seems to be a valid duality. There's also the SP duality that I mentioned at the beginning.
But Brian, it's in the 4D to 3D case, you can have the generic algorithm. So you take the 4D duality and add the KK monopoles. Right? In the reduction from 3D to 2D, you kind of have to like work on a case by case basis.
Yeah. So there's two extra complications. Yeah, you have to work on a case by case basis, and also you have to make a choice as to how you scale these parameters. So I made this choice. Typically, I'll make a choice when I can. I'll make a choice where M is finite, all the masses are finite, and all the Fi terms go as 1 over R. Because this gives me a gauge theory description of 2D. When I'm forced to, by mirror symmetry, I have to consider more exotic limits. But I could also just choose to consider more exotic limits, and maybe you can get interesting 2D gauge that way. But for the most part, when we can, we take the simple.
Do you get interesting? If you take the spin case and present 3D duality and you take exotic limits, do you get different limits?
Yeah, we haven't played with it. But when we can, unless we have to, we take the nice limits. So yeah, let me just, so the SP duality, so there's a 3D, an SP version of this 3D Picasso duality. Level K with NF, 2NF chirals, fundamental chirals, is dual to SP 2NF minus NC, NF plus K minus NC, minus 1. Which you can get from the duality I mentioned earlier by just flowing with real masses. And here K can be half integer as long as NF is also half integer. So there's an odd number of chirals. And you need this relation in this theory in order to not have parity in everything. So this is a window duality in 3D. And so you can try to reduce it. Now if you take K to be half integer, you get a very similar thing. You get some direct sum of SP theories. In 2D. And when you apply this to this duality, you get again a termwise mapping, and that termwise duality is Fourier's duality. Because I've taken K to be half integer, so I get to shift by minus a half that word back. Now, if you take K to be integer, things don't work so nicely. So you can go through this derivation, and you can derive something which looks like a valid duality, and in fact, you can do some checks of it, and it seems to work. For example, the S2 partition functions agree, but it fails other tests. The elliptic genera don't agree. It doesn't seem to be quite true. And there's some subtleties in this theory already in 2D because it has an unlifted Coulomb branch. There's a non-compact Coulomb branch, and so is one of the reasons why Hori didn't try to find a duality in this case. He concentrated on NF odd, where the Marx is lifted. So this is why, one of the reasons why this is still work in progress, is trying to sort out what happens in these kinds of examples. And there's other dualities you can try. You can maybe try non-abelian mirror symmetry in 3D. So far I just talked about abelian mirror symmetry. And see if that gives something interesting. So there's definitely more stuff to do. So the last thing I wanted to say a few words about were supersymmetric partition functions and how you can tell a sort of parallel story to what I've said using them.
What is the 4 to 2 set? 4 to 3, 3 to 2, 4 to 2.
Yeah.
Why is it 4 to 2?
Oh, yeah, so I haven't mentioned this yet. I'll say something about this at the end. This is a separate thing. You can factify on a sphere.
Okay.
I'll say something about that. Right, so just to remind you, supersymmetric partition functions, people have computed these on, so first of all, you couple a d-dimensional supersymmetric theory to some manifold MD while preserving some supersymmetry. So there are some techniques how you should do this. And then you can, now the path integral becomes a well-defined object if this manifold is compact, doesn't have IR divergences. So you can compute the path integral on this manifold. And this depends obviously on the theory, but you can turn on certain background fields, which are usually background vector multiplets, and it depends on certain geometric parameters of the manifold. So in general, it's some intricate function that you can compute, and the way you can do this computation is using localization. So the path integral can be shown to localize to a finite dimensional integral, typically some matrix model over PPS field configurations. So these things can be computed exactly in many cases. I'll give some examples in a minute. So the way I want to use it here is we want to consider, so for the reduction, it's nice to consider partition function on SD times S1. And then take the radius of S1 to be tau, where I'll work in units where the radius of the SD is 1. So I compute this for some theory. So I start from some UV description. This UV description analysis, this one. And an important property of these partition functions is that they're RG invariant. You can compute them from using a UV description, and you get the same answer as for the IR description. So in this chart, you can move horizontally very easily. And now we want to study the limit of this as tau goes to 0. And I claim that up to some divergent factor, depending on tau, and maybe some of the background fields which are suppressed, you get the SD partition function of the dimensional reduction. So this factor, I mean, you might ask if this is well defined, because this is some finite piece times some divergence. But this factor can actually be understood pretty well, because it's related to certain anomalies of the equals one-dimensional theory. And so we can understand this, and we can just strip it off and get this finite piece. And then again, using this RG invariance, this is equal to going backwards along this line, the partition function, so up to this factor, the SD partition function of T hat. So if we can understand this limit analytically, and in particular if we can read off from this function some UV description, so I'll show what I mean by that in a minute, then we can use this to help guess what the T hat is, maybe get an algorithm for finding it. So
Why are the partition functions RG invariant? Why are they only sensitive to the low energy
Well, this is an index.
Oh.
So in this example, it just follows from the fact that the index is independent and this is not protected. In general, yeah, it's just a general fact about these partition functions related to the localization argument. Basically, it's independent of the d terms in the action, and so as you flow, these d terms are changing, but the partition function is not sensitive to them. So there are examples where it does. So, for example, the S4 partition function depends on the gauge coupling, so it's not argument independent. But all the examples I'm going to consider are. So, okay, so let me first apply this for the 4 to 3 story. So the object we consider here is the 40 index, or which has. Let me first give a trace formula. So for simplicity, for the experts, I'm going to set these parameters equal. Make things easier. You can take the not equal and it doesn't change things further. So it depends on some fugacities, and for I'll write what how they enter in a minute. So when I set these equal, these just couple to this sum of the energy and the R charge, this velocity P. And I'm tracing over states on S3, and these mu A velocities couple to this vector symmetry. So I get this function. And as usual, this can be interpreted as a partition function on S3 times S1, where these fugacities, in this case, get interpreted as follows: P equals Q equal to minus 2 pi tau, just because it's coupling to the, to the Hamiltonian. And there's some background R symmetry gauge that you have to turn on. It's this factor of R. And the mu A's are related to some background gauge fields that you turn on. So this is a background gauge field coupled to this vector symmetry. So this is the partition function interpretation of this. Now you can compute this this is computed by a certain matrix model. From this point of view, this is computed by just counting the letters contributed by all the basic fields and then projecting onto the gauge invariant combinations. And from this point of view, it's computed by localizing onto BPS configurations. But however you interpret it, you get the same answer. So schematically, you have an integral over the maximal torus of the gauge fields of some contribution from the chirals. So here, this is the representation of the chirals. So this is, I should say, for 40, n equals 1 theories. And a contribution from the vector multiple. Where these functions are explicitly, but there are certain special functions called elliptic gamma functions. And now I want to relate this to the partition function on S3. It's right up here. And we leave that for a second. So this is the index in 4D on S3 times S1 tau, and the partition function on S3 on the round S3. So you can relax P equals Q, in which case you end up getting a squashed sphere. let's just work with the ground sphere, given by a very localized to a very similar matrix model. Now you're integrating over constant values for this scalar sigma. And it's a function of real masses. And then the basic relation between these is that for chiral multiplet. So if I take z sigma now goes to 0, this goes over to some emergent factor. So this is the R charge of the chiral times the 2D unit contribution of the chiral. So now what we'd like to do is take this limit of this index and see if we can relate it to the ST partition function of some field theory. So the naive thing is to just take the integral, take the limit under the integral and take it at the level of the integrand, and then use this relation. And you find then that the integrand goes over to the 3D integrand of the naive dimensional reduction. This diversion factor, it turns out as long as the theory is not anomalous, it doesn't depend on the gauge, on the integration variable, so that can be pulled out, and you get some overall factor which you can strip off. And you get exactly, each piece is going over each piece here, so you get the theory, 3D theory with the same gauge group and the same matter content. And so this seems to be telling us that by the logic I said before, the T-hat theory is just a naive dimensional reduction, which I claim is not true, and that the duality didn't work when we made that assumption. In fact, if we have a 4D duality, then these indices have to agree. And so this, by taking this limit, they have to agree for all tau, so the partition functions in 3D have to agree, and it seems to be saying that the partition functions in naive dimensional reductions agree. And I told you those theories weren't dual, so this partition function was just not powerful enough to disprove that duality. So it turns out that well, I was a little too fast. So when I refine by flavor symmetries in 4D, I should only turn on these new rays, obviously, but it's important, Fugassi's for non-anomalous symmetries. So you have various symmetries which are symmetries of the classical action, but which get anomalies in quantum theory. Whereas in 3D, there's no anomalies. So when I compute, what I mean by the partition function of the naive reduction is the partition function with the most general real mass background turned on. And that we don't get from 4D. We only get the subspace, which from 4D of those real masses corresponding to symmetries which were non-anomalous in 4D. So we only get a subspace, an identity of these partition functions on a subspace. And you can check that they do agree on that subspace, but as soon as you go off of it, they stop agreeing. But now, this is telling us that there's, well, you might take this as a suggestion that there's some effect which is breaking the symmetry in 3 dimensions. And in fact, this monopole operator in the superpotential, this gets charged under flavor symmetries, and it's charged under exactly the symmetries which are anomalous in 4 dimensions. So this monopole superpotential, which we've added by hand, exactly breaks those symmetries. And so we should really interpret the object we get from taking the limit of the 4D index as the partition function of this theory, which is the superpotential. And indeed, then the partition function is consistent with the duality that we suggested. So now let me very briefly tell the same story from 3 to 2. Well, I won't write that much, actually. I just want to say that we can go through the same argument from 3 to 2. So now we should study the S2 times S1 index and study how, as tau goes to 0, this goes over to the S2 partition function of the 2D thing. And everything I said before goes through. You can write it as a matrix model, and you find that the individual pieces reduce as tau goes to 0 to the individual pieces building the S2 partition function. So once again, you are led to this wrong conclusion, as we've seen, that the t-hat theory is the naive dimensional reduction. So what did we do wrong this time? So now there's no anomalies. As I said, in 3D there's no anomalies, so that's not going to save us. But now the problem was that it was wrong to take the limit, to exchange the limit in the integral. So there's no we were lucky in 4D in the fact that we were okay with doing that. But here it's just wrong. And as a very schematic way to see that, I claim that we end up the S2 times S1 tau index, and I put the big quotation marks on this equal sign, is given by some integral over this sigma of e to this w effective of tau that I computed before. Functional sigma. From something like 0.5. So these quotation marks are because this is not really an integral, it's an integral and a sum, because sigma is actually quantized. The imaginary part is quantized because it's related to monopole flux on the S2. But very roughly speaking, this identity is true. And so we saw that in order to, that in certain cases there were saddles of this function which were running off to infinity, where sigma had to be scaled as 1 over r, or in this case 1 over tau. So what I claim is that in those cases, we can do all the analysis with the crystal superpotential, and what it tells us to do here is to change variables. So for example, I'll change sigma to y to 2 pi r sigma plus log pi tau, sigma plus log tau. And if I do this change of variables, now I'm correctly capturing all, this was in the mirror symmetry example, now I'm correctly capturing all the contributions. They're not escaping off to infinity. And so now I'm justified in exchanging the limit and the integral. And then I correctly derive the S2 partition function identities for these 2D dualities. So there's an equivalent analysis you can do by just studying these integrals, but it's a lot simpler to just study the effective superpotential. So that's basically all I wanted to say. Let me just mention a few extensions of this. So, first of all, so we've done 4 to 3 and 3 to 2. We could think about 5 to 4, 2 to 1. These are maybe the 2 natural next things to do. And there are interesting one-dimensional dualities that we can try to derive. And this would be a very interesting story to derive any of those 2 dualities from 5 dimensions. But we haven't done much on that yet. Another...
But the 5 dimensions of the duality, there are no diagonals.
Yeah, so it's a little bit trickier.
Do you think there's some story here?
Well, yeah, I think there should be some story. I mean, well, at least the level, so we could study, say, the S4 times S1 partition function and limits of that. So you should get some identities by studying that and think about what the physical interpretation of it is. And you could also study you can compute an effective prepotential for a 5D theory on a circle. Maybe it's even simpler to study that out here. Another thing to do is to compactify by more than 1 dimension. So compactify on some k-dimensional manifold. And here you have much richer story possibly because this manifold can have non-trivial topology, and you can put non-trivial fluxes on it, and so there should be a much richer story. And as sort of a first step in that direction, that we had this paper from a few months ago, where we compactified for the n equals 1 theories on S2. So say S2 times R2. And here we do a topological twist, so we put some flux for an R symmetry on the S2, which preserves, in order to make some of those supercharges scalars on the S2, and it turns out that X preserves half the supersymmetry, and you end up with a 2D n equals 0, 2 theory. And this can be studied very conveniently using the S2 times T2 partition function that we recently completed. And you find some nice things. You find n equals 0 to some new n equals 0 to cyber dualities. And find for every n equals 2 theory in 4 dimensions, you get an n equals 0,4 theory in 2 dimensions. So there's some n equals 0,4 version of the class S theory that is interesting. And there's also an n equals 2, 2. If you twist slightly differently, you can preserve different supercharges within n equals 2 story. So I think, so this is one example, and I think it would be interesting to also consider more general Riemann surfaces and what theories you get that way. And I think that's all.
If not, well, let's thank Brian again.